In this video, I am going to find a series solution for a differential equation that has singularity in it. The equation that we are considering is this: x square y double prime plus xy prime plus x square minus 4 times y is equal to 0. This differential equation actually has a special name. It's called Bessel's equation, which has the following structure: x square y double prime plus x y prime plus x square minus alpha square times y is equal to 0. Here alpha, by the way, is a constant. And this constant, by the way, could be real or complex. Now, to solve this problem, we follow a straightforward standard process. The first step in the process is to take this differential equation and express it in this format: y double prime plus p of x times y prime plus q of x times y is equal to 0. Basically, get rid of the coefficient that comes with y double prime. So in this problem, the coefficient is x squared, right? So we can go ahead and divide both sides of this equation by x squared to get this: y double prime plus 1 over x, y prime plus x squared minus 4 over x squared times y is equal to 0. That obviously gives us the functions p of x, which is the coefficient of y prime, that is 1 over x, and q of x, which is the coefficient of y, that is x squared minus 4 over x squared. Now, we obviously notice that the singularity is at x naught is equal to 0, the point where the singularity is. Now, is this singularity a regular singularity or irregular singularity? The way to find it out is to take the limit. Take this limit and this limit. What is the first limit? Limit x approaches x naught. X naught is the point, singularity point. X minus x naught times p of x, the p of x that we got here. If we take this limit, if it exists, as well as the second limit, which is limit x approaches x naught, x minus x naught whole square times q of x, which is this, if that limit exists as well, then the point x naught will be called a regular singular point. Please do keep in mind that both of these limits must exist for x naught to be a regular singular point. What does it mean for the limit to exist? It basically tells you the following. If the limit exists, the function, which is this x minus x naught times p of x, is analytic at the point x naught, which means that it is differentiable in the complex plane. The same thing here. This limit exists means that it is analytic at that point, and again, analytic means is differentiable in the complex plane. Now, since our x naught is 0, so we take the limit x approaches x naught, x minus x naught, but x naught is 0, so x times p of x 1 over x, and the limit is 1. Similarly, for q of x, okay, so this is my q of x times x squared, and I take the limit as x approaches 0, and the limit is 4. So both of these limits exist. Therefore, this point x naught is a regular singular point. In this case, x naught equal to 0 is a regular singular point. I could put an x naught here. Now, if you are dealing with a singular point that is regular, the solution, the format of the solution is this: y is equal to x to the power r times summation n is equal to 0 to infinity a sub n times x to the power n. By moving the x to the power r to the right, or within the summation notation, I get y, or y of x, is equal to summation n is equal to 0 to infinity a sub n times x to the power r plus n. Now, I have y, so what I'm going to do, I'm going to find y prime. What is y prime? It's pretty easy. Take the derivative of the series. So it's going to be a sub n times r plus n times x to the power r plus n minus 1. And y double prime is going to be the derivative of y prime, which is going to give you r plus n times r plus n minus 1 a sub n times x to the power r plus n minus 2. This is straightforward, taking the first and second derivative of the series. Now we have y prime and y double prime. So this should not be there. Y prime and y double prime. And we are going to go ahead and plug in those values into this equation. If we do that, we get this. So which is x squared times y double prime. But I found the y double prime right here. I just plug it in. Then x times y prime, my y prime is right here, so x times y prime plus x squared. So now I'm going to do a little bit of algebra here. X squared minus 4 times y is going to be x squared y minus 4 times y, right? So x squared times y is this, which is right here. I just put it there, minus 4 times y. 4 times y is going to be this, is going to be 4 times y. So negative 4, then negative 4 times y is this value. Now, if you look at the summations here, you will quickly notice that the exponents of x is r plus n for few of them. And we are going to combine those. So look here, you have x squared and x to the power r plus n minus 2. So if you combine those, your exponent for x is going to be r plus n. And similarly, you have an x here, and if you combine it with this one, it's going to be x to the power r plus n. So I could combine these two terms. And then also note this term, negative 4 times summation n is equal to 0 to infinity a sub n x to the power r plus n. This one also has the same exponent. So these three summations could be combined to get one summation, and then the other summation, if you look at it closely, it has x to the power r plus n plus 2 because of this x squared. Okay, because of this x squared. All right, now notice the difference between these two. So x to the power r plus n and x to the power r plus n plus 2. So those are not the same. And we want to have the x's having the same power on the left hand side. And we can easily do so by doing a shift of the indices. The way we do it is basically by replacing n by n minus 2. So in this equation, I'm going to replace n by n minus 2. So what I'm going to get is this. This n is going to be now n minus 2 is equal to 0 to infinity, right? This a sub n now is going to be a sub n minus 2, and x to the power r plus n, but n is going to be n minus 2. So instead of this, I'm having this, then plus 2. That's going to make so these two are going to cancel out. That's going to make x to the power r plus n. So now n minus 2 starts from 0 is equivalent to saying that n starts from 2. And that's exactly what we've got here. N starts from 2 to infinity, a sub n minus 2 times x to the power r plus n, and that is going to be the shifted summation. Now, we kind of want to make sure that both the left summation and the right summation starts from the same place. This one starts from 2, but this one starts from 0. So what we need to do, we need to take into consideration n is equal to 0 and n is equal to 1. So we are going to strip off the first two terms for this series, then they're going to align. Now let's go ahead and evaluate for n is equal to 0. So this one starts at 2, so we don't need to worry about this guy. So ignore that. Just only this one. For n is equal to 0, what do we get? R plus 0, so r square minus 4 times a sub 0. And on the right hand side, everything is 0. That means any coefficient of x on the left must be 0. Now, r square minus 4 times a0 is equal to 0. This is basically product of two numbers, correct? But a0, that one cannot be 0. So therefore, we are left with r square minus 4 is equal to 0, which is going to give me solutions r1 is equal to negative 2 and r2 is equal to 2. R square minus 4 is equal to, in case if you forgot, r square minus 2 square is equal to r plus 2 difference of squares, right? R minus 2 is equal to 0. That gives me two solutions. R1 is equal to negative 2 and R2 is equal to positive 2. Now, we are going to have to do the similar process for n is equal to 1 as well, because we want to align it with this guy, n is equal to 2. So for n is equal to 1, what do we get? Again, we plug it in right here. It's going to be r plus 1 whole square minus 4 times a1. And if you factor it out and simplify it, this is what you're going to get. R plus 1 whole square minus 4. By the way, that is not going to be equal to 0. Why? Because we found r is equal to either 2 or negative 2. In neither of these cases, this equation holds true. That means r plus 1 whole square minus 4 is equal to 0. In neither of these two cases. For either of these roots, this doesn't hold true. Okay? So that means that right away makes us think that, oh, it must be the case that a1 is equal to 0. Okay? So from the condition n is equal to 1, we find that a1 is equal to 0, which is going to help us down the road. Now, for n greater than or equal to 2, we could just combine these two summations. So these two summations, this one and this one. Now, we can see that for n is equal to 2 to infinity, or n greater than or equal to 2, these two summations are having the same coefficients. So basically x to the power r plus n, x to the power r plus n. Now both of them starts at 2. So we can combine the coefficients on the left, okay, and compare it with the coefficients on the right, which is 0 in all the cases for all coefficients of x. So if we combine the coefficients on the left, we are going to get r plus n whole square minus 4 times a sub n, which is just this. And the next one is a sub n minus 2. And these two added together must give you 0. And remember, this has to be true only for n greater than or equal to 2. Now, if I solve for n, I'm going to get negative a sub n minus 2 over r plus n whole square minus 4. Now, there is an interesting scenario we have to consider here. Both of our roots for initial equation are integers. So that means the difference of two integers is going to be also an integer. If you are faced with a scenario such as this, there is a theorem that says that we are guaranteed to have a solution for the root that is bigger, okay, or the higher root. Once again, if the difference between two roots is an integer, it is guaranteed to have a solution for the higher root. There may or may not be a solution for the smaller root, however, okay? And that you have to further investigate. Since we know that for the higher root, it is guaranteed to have a solution, we are going to consider R2, which is 2. The other one is negative 2. Now, if I plug in R is equal to 2, right? Right here, this is what I am going to get. A sub n is equal to negative a sub n minus 2 divided by 2 plus n whole square minus 4. Now I can simplify it a little further. That's gonna give me n times n plus 4. By the way, there is a typo here. It should be n, not r. So n times n plus 4. And all of this is true for n greater than or equal to 2. Look at this summation. Look at this summation where it starts at n is equal to 2. So now what we are going to do, we are going to go ahead and try to find the values. Okay, values of these coefficients using this recursive formula. So we are going to consider some of the values 2, 3, 4, 5, 6, etc. For n is equal to 2, this is what you are going to get. So just plug in n is equal to 2 in this formula. It's going to give you a sub 2 is equal to negative a sub 0 over 2 times 6. For n is equal to 3, is going to be a sub 3 is equal to negative a sub 1 over 3 times 7. However, we found previously that a sub 1 is 0. Remember when we set n is equal to 1 and tried to solve for the coefficient, we found a sub 1 is 0. So a sub 3 is going to be 0. And similarly, a sub 5 is going to be 0, a sub 7, a sub 9. That means all the odd subscripted coefficients are going to be 0. So we don't have to do those calculations. So from now on, we are going to do the calculations only for even subscripted values. So a sub 4 is going to be negative a sub 2 over 4 times 8. And a sub 2, we found it right here. And we are going to take that value and plug it in. That's going to give me this. Similarly, we find a sub 6 in terms of a sub 4. But a sub 4 is something we just found. We are going to plug it in. And that's going to give me a sub 6 in terms of a sub 0. So look, all of these coefficients, a sub 2, a sub 4, a sub 6, all of them are finally converting to something that depends on a sub 0. Or you can express them in terms of a sub 0 multiplied by some constant. A sub 8, by the way, again is negative a sub 6 over 8 times 12. And then a sub 6 is something we just found, we plug it in. Now, in general, a sub 2n, that means we are considering even subscripted values, is going to be negative 1 to the power n times a sub 0 divided by n factorial times n plus 2 factorial times 2 to the power n minus 1, where n is equal to 1, 2, 3, 4, etc. Now, what I'm going to do, I'm going to take these coefficients that I found and the general term and plug it into the series here. Okay? Remember, our assumption was that y of x is equal to x squared. R is equal to 2 here, right? X squared times summation n is equal to 0 to infinity a sub n, right? Now, if I simplify it a little further, so x squared is right here. Then for this series, remember a sub 0, the first term. A sub 1 was 0. A sub 3 was 0. A sub 5 was 0. All the odd subscripted coefficients were 0, right? Now, I could go ahead and express the even subscripted coefficients this way. Summation n is equal to 1 to infinity, negative 1 to the power n, a sub 0 divided by n factorial times n plus 2 factorial times n 2 to the power 2n minus 1. And this is exactly what we've got right here. And if I simplify it a little bit more, just factor out the a sub 0 is going to give me y of x is equal to a sub 0 times x squared times 1 plus the summation of this, which starts from 1 to infinity. Now, this is how you will find the solution when you have two initial roots that differ by an integer. So if it is differing by an integer, the higher root is always guaranteed to have a solution, but the lower root or the smaller root may or may not have a solution. Now, this actually needs further investigation. For R1 is equal to negative 2. You kind of have to go through the similar process and try to see if you have a solution for this. However, I will not be doing it here, but I have given you enough tools here to try it on your own if you'd like. And if you follow the same process that I followed so far on this problem, it should give you an answer, or it should give you some idea whether the solution exists or not. This was rather a lengthy problem, so don't get frustrated, don't give up. If you don't understand it the first time, watch the video maybe 3-4 times. It will start to make sense. It's not hard, but you have to kind of see the process a few times, all right? Then you will start to feel comfortable with it. I hope that this discussion was helpful. Thank you very much.